Okay, so like Raj said, I got my PhD from Georgia Tech in 2004. Woo. Any takers on how long it took me to get that PhD?
1 year.
You ever heard of the 10-year rule? I broke it. I actually barely made the deadline, although at that point they didn't even remember the rules anymore, so they were fine. It was in electrical and computer engineering because in 2004 data science wasn't really an accepted term, and machine learning hadn't really percolated into the EE department, at least not strongly. So in actuality, my thesis research was an application of anomaly detection, and we'll talk about that today. So the topic's interesting to me, and hopefully I can convey some of that. I put up here my contact information, and I'm an open networker. That's a term I just learned, so it's trendy. So if you have any desire at all to connect virtually or in the real world to talk about today's talk or anything, or just send me a nice little email on something random, please feel free to do that. And you can also connect with me through LinkedIn. Normally I don't do agenda slides, but I think there's enough today I kind of want to set your expectations. Of course, we'll begin with talking about anomalies and why it's important. And then I'm going to pitch to you a data science fairy tale. This is a toy problem that I came up with the last couple of days to sort of show how we would do anomaly detection and make it a little more palatable for some of our non-data science friends. That leads into advanced topics in anomaly detection, which I won't really dive into, but I'll talk about, and you guys can follow up in the question session if you want. And then I'll present seizure detection as a real-world example of anomaly detection. This was my thesis research, which continued with a postdoc and a commercial application. So let's start at the beginning and talk about anomalies. They're very intuitive and they're everywhere, and this dictionary definition suits us pretty well. There's just something that deviates from the normal. And the important part to keep in mind here is that if we want to call things anomalies, we have to have an idea of what normal is and what deviation is, and that's the essence of the machine learning side for anomaly detection. It's no coincidence that there's an apple there because we're going to talk about apples today. So anomalies are interesting. We don't want to just detect everything that's unusual. We want to detect things that are unusual and interesting. So here are two examples that I pulled to illustrate that. The one on the upper left-hand side is from an anomaly detection technique that was published around 2000. These are images of handwritten character digits that are used for benchmarking machine learning and computer vision challenges. And as researchers explored this over the years, they began to plateau in their performance to about the 97% level in terms of accuracy, and the joke became that the data was wrong. So it became very natural to run an anomaly detector on it. These are some of the top hits from the anomaly detector, and the ground truth in blue below it, you can see that indeed some of these digits are probably wrong. The second example is one of my favorites, and it comes from the stock market. Volkswagen in 2008 experienced a short squeeze. How many of you guys know what a short squeeze is? Well, you can buy stock or sell stock, and people who speculate on stock going down sell it. They might short it. And sometimes there are events in the market which cause a run on the shares. There's only a finite number of shares available, so all the people who sold the stock short have to cover their position by buying shares. So if the shares aren't there, it drives the price up. In October of 2008, Porsche owned a huge position in options, which they said they were going to convert into stock shares. So they were going to go buy up all available float. I think the calculations put it at something like 99% of all stock shares would be accounted for with this transaction. So the stock price rammed up from 200 euro to over 1,000 euro in about a day and a half. So it'd be great if you could detect this in real time, but even forensically, it's kind of interesting to go back and see what happens in the markets. Anomalies aren't just interesting, though. They're valuable. They have intrinsic value as business, science, research, etc. Here are a couple of common business examples that you're probably familiar with. I think credit card fraud is maybe the canonical example of anomaly detection. I got hit by credit card fraud recently, apparently buying $1,700 of wine in France. I got the alert sitting in my living room in Roswell after buying something online in Roswell. So it's a tough problem, but it's useful. And it's not just credit card fraud. It can be insurance claims, prescription fraud, things like that. And it doesn't always have to be negative. Sometimes we're interested in good anomalies. So you might be running a marketing campaign and see a cross-sell or an upsell that results in unusual spend, and you might use anomaly detection to track that. Video surveillance is one that I found pretty interesting when I was researching some of the latest literature for this talk tonight. You know, we live in a very monitored world, and there's an enormous amount of effort in automating the analysis of video. And it's kind of an open-ended problem because what's something bad that happens in video, right? It could be traffic, it could be intention, it could be gait, it could be someone's gait when they're walking. It could be an object that's left somewhere an unusual amount of time. So anomaly detection shows up a lot in video surveillance. In this case, I think this is traffic on the Bay Area freeway, so it can be used to tell you when you should go home or not. Email, we probably all received a classic letter from some ousted Nigerian king who's looking to restore his kingdom. So it's familiar. But what makes it an anomaly is more than just the content or the recipient of the message. It's also the flow of the messages across the graph of users, email users. So it's an anomaly from my point of view because I normally don't get email messages from this domain or this user. I don't get email messages with this kind of content. But it's also an anomaly from the internet service provider's point of view because of the mailing schedule and the content in the recipient list might be particularly large or unusual. My favorite part of anomalies are that they're expensive. Now, not all anomalies are expensive, but when I say expensive, there's two axes here. The first is it can be very costly or even impossible to obtain examples of anomalies. So in Machine Learning 101, the first thing you think about is differentiating two classes of objects, good and bad. But sometimes you can't do that. For instance, let's look at condition monitoring. If you have a wind turbine that crashes and breaks and burns and costs you, $10 million to repair, an outage, and other expenses, you can't just go find crash-burned windmill turbines, and you can't just find them before they actually break. So you have to think about approaching the problem from the point of view where you may not have counterexamples from the class that's normal. They're expensive in another dimension too, in that if you don't detect the anomaly, it can be very costly. So the couple examples up here, you can see counterfeit bill detection for protecting national currency. You can imagine numerous examples in medical domain in terms of research, claims, discovery. And then my little pet favorite down here, which are seizures. So we'll go over that one. As an aside, I'll mention that I had a student come to me during one of these talks a couple of years ago and tell me they had seen an episode of some TV documentary that discussed counterfeit detection of US currency. And apparently the Secret Service they do anomaly detection by human anomaly detector, which I thought was pretty interesting. Of course, I'm sure they have automated stuff now, but it was an interesting use case. So we see anomalies in all areas of our life, from business to science to research to medicine to communications to machine networks and our personal life. And they come under many different names. Some of these are more familiar than others. But regardless of the name we use, there's one key idea that binds them together. All right? They're rare, and instead of focusing on, they're rare, and in this case, I'm looking at this needle in a haystack problem. Instead of focusing on the hay, instead of focusing on the needle, you focus on the hay. So the idea is that in Machine Learning 101, if we have piles of data that we want to analyze to sift through and find something interesting like a needle in the hay, normally we would try to collect a needle to learn from it. But it turns out it can be more effective and easier to just look at the hay. We'll find things besides needles too. So how do we go about doing anomaly detection? What is it to start with? This is kind of a machine learning signal flow for how we would do anomaly detection. And I've set this up as kind of a classification problem. It's machine learning because the math that tells us how to model the normal and the deviation comes from the machine learning domains. It's an unsupervised classification problem in its purest form. So ideally, an anomaly detection system would be something you could just dump examples to, raw data, without any transformation or processing, and it would just tell you, hey, look here. Of course, the reality, which is why I put the asterisk there, is that no system can be bootstrapped quite like that. It's a classification problem. It's not just a classification problem. There's many different ways to view it, but in the simplest form, I like to think of it as classification because things are either good or they're not. They're anomalous or they're not. If you go through and look at anomaly detection systems in the real world, you'll find that a lot of them don't actually do intervention. So in a typical classifier system, you're running the system to try to detect something in real time or score something or make a decision. But in anomaly detection, you often don't do intervention. Any ideas on why you don't do that? Say that again?
So it ruins your data.
It ruins your data. And also, you might not know what the anomaly is. So for instance, if you've got a video surveillance network in a parking garage doing anomaly detection and you want to intervene, you're setting this up to detect creeps who are stalking people on their way to the car, and you decide to taser them with a taser bank, right? Obviously, you're going to get tagged with a lawsuit on the one case that you do wrong. Somebody else is going to own the building. So in general, anomaly detections are presented as alerts, and they'll be processed either by downline systems, so regular supervised classifiers or something like that, or by people. Another interesting aspect of anomaly detection that's a little different from other machine learning applications, it tends to be batch-oriented instead of online. A lot of this is because the math for the easy techniques for doing anomaly detection require you to have all of your examples in memory and do matrix factorizations and things like that. So going through this, just to touch the point on the diagram here, we start with some data from users and devices and sensors, and we collect that into a database or data store, or we may stream it real time. And then we extract features from it, because we usually don't want to process the raw data in its natural dimensionality. And then we run a detector, which is a classifier, which generates our outputs and tells us whether something is anomalous or not. And one thing that I show on here is that your system doesn't have to stop at that. You can have a feedback loop so that you can take the results of your anomaly detection and improve the system. And one of the examples from one of my clients that I've been looking at is in bank transactions. If someone keeps getting flagged with an anomalous spend and an analyst keeps going and overriding and saying this isn't actually an anomaly, at some point I don't want to be flagged anymore, right? So maybe that kind of anomaly detector is a bank change detector because it'll induce you to change banks. Okay, so we've seen some examples and we see what it is. And why do we want to do it? It might be obvious. We'll just go over some of the examples here. The first big motivation might be that data comes as haystacks. So we have far too much data to process compared to what we have time to look at. So we're going to use automated techniques to summarize that. And anomaly detection is one technique which is sort of like a fishing net. It catches a lot of interesting things for us to look at. Well, the second thing is that anomalies are usually important. So unusual, which is an anomaly, usually ends up being something important. And the example is, a jet engine that isn't qualified to make a transoceanic flight, a credit card spend, a seizure, all the examples we talked about before. An interesting one are that models are expensive. So it's not exactly cheap to do anomaly detection. We'll talk about some of the shortfalls. But it's definitely expensive to go build individual models for every counterexample that you want to study in a system. So if I want to detect, say, faulty parts in the space shuttle, and I want to go through top to bottom all of the parts and systems in the space shuttle to make sure that I have a model of what's good and what isn't good, and I build classifiers in a traditional, straightforward manner, that's going to take forever and bankrupt me. Instead, I need something that's going to allow me to focus my attention on the core parts that I'm going to examine further in depth with human intervention. Similarly, the labels are expensive. That's what we talked about before. You can't observe some events like a jet engine crash. Some events are too expensive. You don't want to wait for the space shuttle to blow up on the pad before you start asking, will it launch? So these are all some of the examples that would make you think that maybe you should explore anomaly detection in your next problem. Wouldn't be complete without having the disadvantages, and that's all the disadvantages that we have. So we'll get to those later. All right, so now I want to walk you through an example of anomaly detection with context. So the context is, I want you to meet Bob. Bob's the eighth dwarf. He's in the apple business, and he knows a lot about apples. They had a recent apple incident up in his valley, and they found out that red apples are poison apples, so he wants to make sure that he's only going to sell the healthiest, best apples there are, which are Bob's green apples. The apple business isn't doing so well because they just had a poisonous outbreak in the valley, so he has a lot of free time, which he spends taking online courses on data science. So he decides that he wants to apply this knowledge to the apple problem. After a week or two of classes, Bob decides he's going to do the straightforward classifier approach to detecting bad apples. So everything here is what we're going to look at to see how Bob is going to go through the workflow to determine whether apples are good or bad. So we start with our inputs to the system, and these are the apples. The inputs are real-world objects or instances or items. They could be data already. They don't have to be data, though. That's kind of what makes them inputs. And we start with our inputs and a goal. So Bob has gathered up some sample apples from his orchard that are good, and of course he has that one red poison apple to work with too. We can't run computer programs or algorithms on apples. We have to convert them to numbers. So that process is featurization. So we look at the data and typically decide on some aspects that are going to capture the interesting traits of the data that we know will separate good and bad examples. In this case, there really is a measure called water core. I Googled around on this, and it's a measure of the cellular and water density profile of an apple, and it's actually used in produce packing companies so that they can schedule the packing of the apples for optimal shelf life. So Bob has access to some X-ray device or optical intensity measuring device, and he has a water dunk tank to measure density. He takes his apples, and he makes the measurements, and he plots them in feature space, and this is the data that we can look at to start to build a classifier so we can determine if we have a green apple or a red apple. Along with the examples of the data and the numerical measurements of the features, because this is a classifier, that implies that we have labels for all of the apples. There are no unknown apples. Bob has 14 green apples in front of him and a red apple. And we're going to assign those numbers too so that our algorithm can correctly determine how to classify red and green apples. So in the computer, the green apples are +1s and the red apples are -1s. We pick our favorite algorithm. Maybe we go to Kaggle's website and go look at what the winners did in the latest contest and download something in R, and boom, all of a sudden, we end up with a line. So it's a good use of time. We've got this line, and this line tells us how to classify apples. Everything that's on the left of the line is a green apple. Everything that's on the right of the line is a red apple. This is a classifier. It's a very simple classifier called a linear classifier. All right? You can make this problem more complex. I mean, you can get your PhD in it, right, obviously. But we're not going to go into that here. Bob's excited. He's got an apple classifier, so he puts out a request for apples in the valley. And people sending him in some other examples of apples that he can use to run through his classifier. These are all new examples, so they're test examples. They weren't used in training, so Bob's following the script perfectly from his online course. And when we plot what he has, we can see that he has examples that are correctly classified. On the left, the green apples. We have one green apple from another valley that gets misclassified as poisonous. And we have a few apples that he hadn't even thought of. These are the unknown counterexample cases, rotten apples, worm-ridden apples, etc., that show up in various places. And for this example, are all classified as green apples. So Bob has these results, and he somehow needs to convey to the Executive Council of 8 Orchard, Inc., these are the other 7 dwarfs, how good his detector is. So the straightforward way to do this is to tabulate the results into a table called a confusion matrix, and then derive some statistics for that. The statistics that we want to derive capture the trade-off between perfectly classifying green apples and perfectly classifying not green apples. So if Bob's problem originally was to say, I want a detector that's going to get every single green apple there is, well, that's trivial to do. I just say it's a green apple, right? So we have to balance that with also correctly saying which examples aren't green. So from the confusion matrix, we can take a couple of the cells and compute 3 metrics that are commonly used in these types of problems: the sensitivity, the specificity, and the false positive rate. Now the sensitivity represents our snapshot of the left rectangle, the green boxes, and that's telling us how many green apples we're correctly classifying. We have to balance that with classifying the not green apples, and that's captured by specificity. And sometimes we'll plot these against each other. We won't in this example. The false positive rate is another way to think about how the system performs, and it says, for all of the green apples, all of the labels that I say are green, how many are actually green or not? And this is related to the specificity, so you really only need one of the bottom 2 measures. All right, so that was classification 101. And Bob has a classifier that gets his apples. It's pretty good, but it misses all the cases he didn't consider. An alternative way of thinking about this is if Bob focuses just on the green apples and treats it as an anomaly detection problem. So if we do that, we can study this very simple algorithm called centroid-based anomaly detection with the following diagram. So we start with the examples, which we already have labeled up here. These are the green and the red apples. Forget the yellow one for a second. He's actually a false positive. And we measure the centroid. So the centroid captures our notion of normal. Remember, when we want to do anomaly detection, we have to have a concept of something that's normal and a concept of how something deviates from normal. So we're very literally going to do that here by taking the average apple, which is measured by the centroid, and we're going to take a distance, a threshold, which is represented by the yellow line. And we're going to say that anything that's farther enough away from the centroid to be outside of that line is an anomaly. And that's all there is to it. We have a score for that, which is simply the Euclidean distance or some other appropriate metric, which measures the distance to the centroid. And of course, we'll get some false positives, as indicated by the circled yellow example in the upper left. So this is an easy way to do anomaly detection, and it actually works. In fact, it's used in intrusion detection systems a lot of times because it's really fast. I mean, you can do millions of operations per second on this. But there are issues with it. So right now, Bob has 2 examples, and he wants to compare his techniques to present. And I'm going to there are many different ways you can compare these. I'm just going to kind of go over some that illustrate the pros and cons of anomaly detection. So the first thing that I want to point out is that any machine learning approach to solving one of these problems is dependent upon the features and the models that you use. So, think of a stupid example. I'm going to measure apples. I'm going to use this feature. Does the apple weigh more than 10 pounds or less than 10 pounds? And that's a silly classifier, right? So that's an example of a feature that doesn't work. The reason I bring it out here is because anomaly detection is notoriously sensitive to the correct selection of features. Because you're not deriving your features to separate two particular classes, you're preparing your features to separate you from every possible class that isn't the normal. So it takes a lot more engineering to pick good features in anomaly detection. The next point is labels. So if you have a problem where you can have both examples, both classes available, you may or may not be interested in anomaly detection. But if you can't get the labels, you should consider anomaly detection. And a good example of this is maybe Bob has a cousin who lives in North America who's read about his cutting-edge research in poison apple detection, and he wants to do this himself. He sells apples. Well, he doesn't need a poison apple to build one of these detectors using an anomaly detection approach. A downside of anomaly detection, which I didn't emphasize, is you have magic numbers, more magic numbers than the traditional approach. So if you go and build a classifier like Bob did the first time, the script for building that as a data scientist to make that statistically sound is pretty good. There are little things that we may wave under the sheets every once in a while, but it's not such a hard problem to come up with good answers and justifiable numbers for your parameters for your system. But in anomaly detection, we don't have those same luxuries. It's a little more rule of thumb and ad hoc, so it's a little harder to defend on theoretical bases how you pick these parameters. Since I made this for an anomaly detection talk, of course, the anomaly detection system wins. But in general, it's probably not true that an anomaly detection system would win. In general, anomaly detections are going to give you a lot of false positives. But that's okay because you can combine anomaly detection with something else. Remember, anomaly detection can just be sort of a focus of attention, front end, to some other system. And just for completeness, I put down here the sensitivity and specificity numbers. The anomaly detector, in this case, dominates on both numbers, which is why I would say it would win. If it was a mixed bag, who knows which one's better. And who knows if this is really good enough, right? That's up for the dwarves, the Council of Dwarves, to decide. Okay, so the first question that we want to ask, looking at and saying that we like anomaly detection, is what can we do to improve it? What kinds of issues are there? And we kind of hand-waved for this threshold thing. We could imagine that there would be many situations where you don't know how to pick that threshold. So there are three common approaches that people use right now. There's a Tukey statistic, which I show in yellow, and that's basically a function of the interquartile range, if you guys know what that is. The advantage of the Tukey statistic is that it's not parametric, so it doesn't depend on any assumptions about the distribution of the data. So these apples that we plotted here come from a distribution which represents how likely we are to see apples with any given measurement, inside, outside the circle, etc. And we can see that they're densely clustered in the center here. We don't have to make any assumptions about that to use the Tukey statistic as a measure for the threshold. More commonly, though, we'll use something like standard deviation, in particular standard deviation of the distance from the instance to the centroid. And if we do the standard deviation, that's probably not going to give us as crisp of a boundary, and it's going to shift the center point of this ball, which we use to determine whether an anomaly is good or bad. If we're interested in the standard deviation approach, we can use something better than just standard deviation, which is the Mahalanobis distance. And the Mahalanobis distance is sort of a generalization of the standard deviation where we take into account the covariance of the items. And that tells us, in essence, what the standard deviation is, or the variance along the axes of an ellipse or a hyperellipse. So the Mahalanobis distance fits ellipses to our examples and allows us to get tighter bounds. Now, why this is important is because we really like the idea of capturing the dense regions in feature space to call normal, and things that aren't dense are anomalies. And the better we can do a job of describing the dense region, the better we will have performance in our anomaly detector, ideally. So what would an ideal threshold be? So here I've shown these islands that might represent an ideal threshold. And it has some characteristics. It's got to be statistically sound, and it's got to be flexible, and it's got to be based on the density of the observations, okay? But I don't want to take the time to try to model the density of this distribution. I don't have examples, for instance, out here, so I don't want to try to tell you what the probability is of an apple occurring way out here. So I changed the problem into a minimum volume set problem, which is basically find these islands. If I do that, the question is, if I want to do that, how can I achieve that? And there's kind of a golden algorithm that does this automatically, and it's sort of I think, the canonical novelty detection algorithm in machine learning. And that's the one-class support vector machine. So the one-class support vector machine will find given a fraction as its input, it will find the level sets in feature space that will give you that fraction as outliers. So I can say, out of all of these apples, if I want to say 5% I'm going to call anomalies, I can put that into the algorithm, and it will find the region of space that will give me normal, such that only 5% of all future examples will be anomalies. So that's pretty amazing, right? It does that just on the training set. As long as your statistics change, as long as your process doesn't change, you're kind of guaranteed. You know, after 100 apples, I can tell you with high confidence that I'm only ever going to get 5 out of 100 apples in the future that are going to be anomalies. And if I get more than 5 out of 100 that are anomalies in the future, that's another form of an anomaly. That tells me my model broke. So the one-class support vector machine is awesome, and we'll talk about this more in the example on seizure detection, but we won't go into the details right now because it would take too much time. I have to show you support vector machines and then the one-class part. If you are interested, I do have the slides here, and we can go over it afterwards. So that's kind of a whirlwind introduction to anomaly detection, right? The idea is that you step outside of the normal way of thinking about things and you give up on trying to figure out what a needle is and just focus on the hay. There are a lot of issues, though, to do this correctly. The first, which is kind of funny when I read about this, is the impact of outliers. So we're building an outlier detection system, but it turns out that if we have outliers in the system when we're building it, that kind of corrupts things a little bit. So you never really can get away from the problem perfectly. The second thing, which is really interesting, is the examples on apples are great for a little class, but they don't get you very far when it comes time to do an example at work. You probably have richer data sources that include things like graphs. So these would be connections between people or machines or devices, and flows on graphs. You might have spatiotemporal data. So you might look at epidemiology. So you have the outbreak of a disease across different counties in the state. Or in our case, we'll look at seizure detection, and I'll show you a multivariate time series, which is kind of a spatiotemporal example. Or you might have text or other unstructured data, which represents the bulk of the data that's available for us to mine these days. All of these can still be tackled from an anomaly detection point of view. In fact, the best place to start is if you're working this area, well, look at the models that you're using now and then tack on anomaly detection to it in Google, and you'll find how people have adapted these techniques. Okay? If that doesn't work, go find your favorite anomaly detection algorithm and look at how you can transform the data into a framework that you can process using that algorithm. It is interesting, though, that as rich as these are, as available as they are, and as much as you can use existing techniques, it does make the problem a little more complicated in terms of defining what an anomaly actually is. So imagine, for instance, for me, I think about the epidemiology case, or the data science epidemiology. We want to look at the outbreak of data science across the United States. And so I start tracking meetups in different places. How do I know how to normalize that? How do I know what normal data science meetup activity is across different population centers, different time zones, et cetera? So the richer your data source, probably the harder it's going to be to define what normal is. A very obvious thing that we didn't touch on the slide is if you do have labels, like the poison apple, you can always use that to improve your system, right? So don't throw away your labels if you have them. And as you go and implement your system and start recording labels and getting feedback on it, use those too. If you're interested in doing this in online, so you want to go mine the stock market, that example I showed you in Volkswagen, that happens all the time. I mean, there's probably a stock every day that gaps up 20 or 50%. So, if you are omniscient, you're rich in 5 days, right? The doubling periods. So if you want to go implement something like that, then you're interested in online anomaly detection and you want it to be low latency. Now that's not normally how we pose the problem, but there are approaches that talk about this. Another reason you might want to use online anomaly detection is if you have just too much data to deal with in memory. So you got a fire hose. The problem with going with online, aside from the basic matrix factorizations or other implementation details, is it also adds another dimension of complexity to what an anomaly actually is. And that is, how much difference between a past example do I have to observe? How much drift before I call it an anomaly? And some things drift very smoothly and slowly, and so it becomes almost impossible to pick one characteristic timescale that will let you say, this is where something changed. Features, we've already talked about how important those are to the performance of systems, but also there's a relationship to clustering and other techniques. So you may have noticed that in this example here, those look like clusters. And in fact, we are finding, in essence, clusters, but we're not setting up as a clustering problem. So the clustering problem is to take all of your data and divide it into sets, and then tell me about those sets. This is a little bit formulation, so we don't get clusters for the red examples, for instance, and there's no guarantees on how good my clusters are. But it is related, and you can use clustering as an approach for anomaly detection. There are other things too, like change points. When I was talking about the online anomaly detection and how you want to track the system over time, that's a change point problem. This slide is a takeaway for you guys. I'm not going to go through every point, but there was a great survey paper in 2009 in the ACM. It's about 40 or 50 pages, I think, and it goes over, at least in 2009, a snapshot of probably all of the popular techniques for anomaly detection. He breaks it down into a taxonomy, which you see on the left under approaches, and I think he mentions most of these methods on the right. On the right, you'll see that there are extensions which are more complicated, kernel techniques, PCA and subspace methods, etc. The two that are probably specifically developed for anomaly detection are the OCNM and the OCSVM, and those are the one-class neighbor model and the one-class support vector machine model. So if you want to read about hardcore anomaly detection where all the math starts out with that in mind, those papers is what I would recommend. Okay, so let's shift gears for a second. We aren't interested in going into the detailed math right now. We want to sit back and enjoy our beer and see a real-world example. I work on this problem as a data science consultant nowadays, and unfortunately I can't talk about the details of a lot of the anomaly detection for my clients in security and banking and things like that. But I can talk about seizure detection, which is what I did my thesis research on. So this was a problem that I was gifted in 2004 for my thesis research. Our lab group had a long-standing history of working with doctors at Emory and neurologists, and they were studying seizures. And they needed some better techniques to do seizure detection, and throughout the years preceding me and following me, our lab produced several papers and patents and technology that were commercialized in this area. So this is one example that I ended up publishing in the Journal of Machine Learning Research in 2006, and it shows not only the practical example of anomaly detection, but it shows how you would do this with time series data. And a lot of times when you're looking at examples in the literature, you don't see things about time series data beyond ARIMA modeling or something like that. So let's start with some fast facts on epilepsy. Okay, how many of you guys know what epilepsy is? How many of you guys know that because you cleared the slide in 5 seconds before I asked you? Okay, so epilepsy is a neurological disorder. It's characterized by seizures. And seizures are electrographic disturbances in the brain. An easy way to think about it is an earthquake in your brain electrical network, but they aren't necessarily that overt. It's actually any kind of change which impedes your function. It's a little loosely defined because a lot of seizures probably occur that we never observe, because you don't necessarily shake or move or fall to the ground when you have a seizure. I could be having a seizure right now. So it's a big problem in neurology because it affects such a large percentage of the population. 1% of the population worldwide. I guess fortunately for the United States, most of that's outside of the United States in developing countries. But it's still a big problem. The good news is if you have epilepsy, and you may have epilepsy if you even have one seizure in your life, by the way. That's kind of the definition. So if you have epilepsy, they are generally controllable. So you can take medications or try alternative therapies like diet or other alternatives and control your seizures. And control doesn't mean that you'll necessarily be seizure-free. You might be seizure-free, but it certainly means at least a drastic reduction in the number of seizures you have. So a typical patient who would be interested in control might have 8 to 10 or 20 seizures a month. And then if they get titrated on their meds correctly, they might go down to 1 to 2 seizures per year. And that's a big deal, obviously, for the health of their brain, but there's a lot of social and psychological stigma that come along with seizures. So people who have severe epilepsy tend to kind of dissociate from society, and it affects their lives and the lives of those around them.
Can't drive.
Say that again?
You can't drive often.
You can't drive. Yeah, and it's by state. In Georgia, if you have a seizure, you can't drive for 6 months, I think. 70% is controllable. 30% isn't controllable. So what do you do if you don't have controllable seizures? Well, now you're looking at 2 alternatives, which are surgery, which is the preferred standard, or an implantable device, which are experimental and coming online. So in the surgery route, they'll actually go in and profile you. You'll get admitted to the hospital. They'll do surgery and implant electrodes in your brain. You'll be hospitalized for 1 day, 2 days, up to a couple of weeks while they try to record seizures, and they try to record seizures in the right location, and they hope that right location corresponds to where they drilled into your head. If you're a candidate for surgery, they can go in and remove the brain in that region. And it can be anything from something like smaller than a BB to half of your brain. It's amazing how plastic we are. But you can't always do that because not all seizures start with a focus, right? Some seizures, there's no locus of origin for the seizure, so that doesn't help. And some seizures are in areas of the brain that you can't remove, right? So they're critical regions of the brain. So there's still a lot of patients who aren't susceptible or aren't eligible for surgical treatment. And for those, about the only hope are therapeutic interventions through new medical devices. There's one that NeuroPace markets, which is basically a defibrillator for the brain, and it runs a real-time seizure detector, and those algorithms came out of the research lab that I was telling you about at Georgia Tech. And when it identifies a seizure, it shocks the brain, and this shocking causes decoherence of the brain activity, which sort of breaks up the seizure. Kind of like blowing up mountainsides to prevent avalanches, all right? Now, you guys know about that? You know, you set off charges, yeah. So when we study epilepsy, we have some rich data sets that we can use. All these acronyms, you may or may not know what they are. The two that we're interested in are the EEG and the IEEG. They're both EEG, which are electrical measures of brain activity. The difference is where you acquire the data. The standard EEG is measured on the scalp. The IEEG is intracranial EEG, so that means they'll actually drill into your head and place electrodes anywhere from the surface of your brain into the interior of your brain. And they'll do this in multiple locations to record. And the reason we do that is because of the resolution in time and space that we get by measuring that way. It's sort of like looking at a really fuzzy picture versus a 4K digital cinema image on your computer. These three companies are working on devices in the space. NeuroVista, I think, is no longer a going concern, but they went through Series D capital raise and had clinical trial in Australia. And I think the project is still continuing, just not under that company. And I've worked with all of these. So all these rich data sets, and we want to build a seizure detector. Let's start by looking at a seizure. And this is your brain on EEG. So this is actually a patient who has had about 14 electrodes implanted into their brain in 2 different locations. And each of these traces represents the EEG synchronously measured at one of these electrodes. And you can see that they're pretty correlated. This is about 20 minutes in duration, and the marked off region represents a seizure. How do we know that this is a seizure? Any ideas on what we do for that? Basically, epileptologists are gifted with a license that says, I can call this a seizure. And that's how it's measured. If it turns out that it presents physically, then we definitely know it's a seizure. If it doesn't, then we call it an electrographic seizure. Okay? And I quoted the obvious part here because, of course, to you and I, it's probably not obvious that that's actually a seizure. I don't know where I would call the beginning or the end of this. But it is probably obvious to a group of epileptologists, especially since I had them mark this seizure for me. Another thing I want to point out on this is these are time series values, okay? And time series data is funny in that we can probably recognize patterns in time series if we look at them long enough. But it's not the best representation of time series data to look for changes. So if I have a time series like this, I probably don't want to look at just a time series. I probably want to look at in the frequency domain or a spectrogram or something like that. Turns out that epileptologists don't do that because spectrograms are too dang fancy, but they could do that if they wanted. Okay, so if the problem is to detect seizures, let's talk about what people did before and what we would do in this kind of work. So in before, there's this implicit model of brain electrical activity that says that for a person with epilepsy, your brain goes through 3 states. It has baseline activity, and we're not going to call it normal because it's not necessarily a normal, healthy brain, but it's baseline activity. And these are all the things that we're probably not concerned with. And then we're going to invent something called the pre-seizure regime, which is a magical period that no one measures, but it's the part of the time series that comes right before a seizure. And it's very subjective, and it's ad hoc, and it's not really clear that there's anything special about this regime. And it's not clear if it's special if it's 5 minutes before a seizure or 2 hours before a seizure. And then we're going to measure the third class of items, which are seizures themselves. This is a very stereotypical seizure to illustrate the point that it's kind of like an earthquake. But in general, they don't have to be that obvious. I mean, if you go back to the slide before, they can be pretty subtle, right? So we take these 3 states and we collect data and we build a traditional classifier. And generally, it's a binary classifier. There's a seizure and there's not a seizure. Now, the problem with this is the same problem that we have, which would motivate us to do any anomaly detection system. First, seizures are really expensive to collect. I have to basically go find candidates for surgery, do surgery on them, hospitalize them, monitor them, collect the data, and pull it out. That costs a lot of money, all right? Second of all, I've perturbed the system when I'm measuring that data. When you go in to be evaluated for a seizure, you've had major brain surgery. So you also have seizures because of that, right? Third thing, the quantity simply isn't there. Even in the busiest epilepsy centers in the United States, they only do on the order of tens of surgeries per year. So your total sample size for seizure patients might be 10 or 20 for any lab group, and it might be on the order of 100 to 200 total in the United States for all the collected data that people have had. And you complicate it further by the fact that we have enormous class imbalance. A typical seizure will last for 2 minutes or less, and you might have a couple of seizures a year. And it might not occur in every region of your brain, but I might record 256 channels for you as long as you are under observation. So I might have a fraction of 1 in 10,000, 1 in 100,000, 1 in a million instances that are actually labeled seizure. So that automatically sets us up for failure in the traditional classification framework. It makes it challenging. At minimum, it's a challenging class imbalance problem. Well, when I started researching for my thesis to see what topic I was going to do, I was reading about anomaly detection, and I came up with those metrics that we saw in the beginning slides. You know, anomalies are rare, they're interesting, they're valuable, they're expensive, and of course, immediately it comes to mind that maybe seizures are a good way to a good application of anomaly detection. And so I decided to try to do this. And I posed the problem by saying that basically we're going to have baseline electrographic activity and everything else. And we're not going to care about what goes into the everything else bucket. So it's a classic anomaly detection. We're going to run this and we're going to see. If it turns out that we can pick features so that the everything else bucket is just seizures, then that's a win right away. If it turns out that we get back seizures and artifacts and other rare events, then we might need to tack on something else to the system to make it work better. Okay? And this was kind of counterintuitive at the time. One last note, novelty detection, which is on the title of the slide, is a specialized case of anomaly detection. It's subtle, but novelty detection simply means that you've trained and built your systems only on the normal examples. So you deliberately prune out examples that aren't normal. Okay, so if we want to run this on time series data, and we remember back to the Apple problem for a second, we need to convert our inputs, in this case their time series, into features. Okay? And there's a standard idiom for doing that in time series signal processing, and that is to run sliding windows over seconds of the signal and take measurements. So the idea is we have this rich serial correlation in the time series, we have a lot of information, but it's not represented in a form that's going to be easy to learn, and it's too much data. So we take these windows, in this case, they're 1 second windows, and we slide them over the time series, and at each example in time where we slide the window, we measure. What do we measure? We measure 3 measures of energy. All right? These are chosen. I'll talk about that in just a second. But we measure these 3 energy measures, and we record the label that goes with it. So in this case, this might be normal EEG, and we might have some numbers. It might be normal EEG, we might have some numbers, normal EEG, etc. Once we do that, we're left with a pile of feature vectors and a pile of labels that we can plug into our standard classifier systems for anomaly detection. So there is an interesting question here, which is how do we pick those features? Because I told you that the success of an anomaly detection system really depends on what features you use. So we have some domain knowledge from the epileptologists and scientists who have gone before us. And the domain knowledge is that seizures tend to have this chirping type of behavior in time frequency, which means that their frequency changes rapidly over time, especially with respect to other types of EEG behavior. So you can canvass the literature and go read about different features that people use to detect chirping. There's entire PhD theses on how to detect chirps. But if you just want some quick and dirty features, these are 3 that work. They're computationally efficient, they're just sliding windows, and they're easy to plug into a large-scale EEG data mining problem. So how did it work? Well, hopefully it worked pretty well because I'm here today. If it didn't, I might be going for the 20-year rule. So I have here some plots of the results. The top chart is actual EEG data from the baseline epoch. And unfortunately, this plot was generated to show the performance of the detector over minute-level timescales. So you can't really see the fine-grained behavior of the signal. So it just looks like noise. But if I was to blow that up, so this is 15 minutes in time. If I was to blow that up, you could drill in and see all the little waveform idiosyncratic behaviors that you would recognize from the previous slides. On the bottom slide, I have a running output of the detector, which has been normalized to give us sort of a probabilistic measure of alarm. And we set the threshold to be 0.8 for reasons that are discussed in the paper, and you can see that the alarm doesn't trigger, okay? So this is good, right? I mean, this is normal brain behavior, it's baseline, and it behaves normally. And this example right here is run off of baseline EEG that the system had never seen. It had never seen a seizure, and it had never seen this baseline, and it didn't know how to discriminate different patients or anything. So that's an encouraging result. How does it work on seizures? So it detects a seizure right away. And I want to point out a funny little story. I was giving this talk in a neurology class at UPenn, and one of the students said, yeah, but I could just draw a line and detect that seizure. And he's true. It's correct. You could on this example. But there's 2 points I'll tell you why that's not actually a good comparison here. The first is that that line that you see here is only for this type of seizure, and we've already said that there are many other seizures which aren't discriminated by their amplitude. And the second is you can see the behavior of the detector after the seizure onset. So it continues to call it an abnormality after the seizure has already decreased in amplitude. So what's really going on here is these features aren't looking at amplitude, even though it's obvious to us in the eye that this seizure is marked by big amplitude changes. It's actually looking at the shift in the feature space, okay? And this detector ended up achieving state-of-the-art when it was written, which is something like 95%, with a certain latency measure, which was about 2 or 3 seconds after the seizure. So you could use this in a real-time device, okay? And I'll mention one other little anecdote. When I was writing the paper for JMLR and I was reporting the results of 95% or whatnot, some of the papers that I referenced had results of 99, 100, 120. They had ridiculous performance numbers. And we implemented all these algorithms in our lab. But it turns out that epilepsy researchers do a lot of selection bias when they're writing papers. And so they only pick the very best examples, right? So there is no shootout in seizure detection because nobody wants to drop the kimono. But if there was a shootout, a good detector might be 90% these days or 95%. And I expect this one would go down a little bit too. So because this was research for my thesis and my postdoc and work to continue, we got to spend a lot of time exploring different aspects of it. So we kind of dug into how it works. Some of these details are in that paper that I mentioned, the JMLR paper. This is a figure that kind of shows it, though, I think, nicely. These are the marginals for the features on the top for the interictal regime, which is the baseline, or normal brain behavior, and the bottom, which is the seizure regime. So you can see clearly that the features change with a seizure. And so actually that was something that was another investigation for this paper, which is how much of the performance of this detector had to do with the anomaly detection and how much had to do with how well you picked your features. And the answer is it's coupled. And if you were to read the paper, upon revision, we actually implemented a Mahalanobis-based detector, which did pretty well. It was comparable, but it wasn't the same. So I think the short answer is in anomaly detection problems, it's always going to be the case that if you have great features, you're going to do much better than if you don't. So I'll just wrap up what we have here. You've already seen the advantages. You might be interested in anomaly detection if your problem fits one of these haystack situations, or if you can't get examples because they're really expensive, or you don't have any data scientist budget laying around. Anomaly detection's for you. But if you go with anomaly detection, be prepared for the challenges. As we mentioned, I can't stress it enough, features for the world, right? The better the features you have, the better your results are going to be. It turns out that if you dig into this, I've kind of glossed over what normal is. And this is coupled to features and the technique that you use for anomaly detection. But it's very critical that you have a good model of normal and that you have good data sampled from normal situations. And deviation, you have to have a model for that too, and there's different approaches. We saw in the recap and the statistic and the ACM survey slide, they break down the different techniques for anomaly detection. A lot of those different techniques have to do with how you measure deviation. Together, the normal and deviation part cause you to have some magic numbers. We mentioned that magic numbers are important to the system. So this is how you tune an anomaly detection system. You can't just do cross-fold validation or something if you don't have any labels, right? So it becomes a challenge. If you go try to buy an anomaly detection system or build it yourself, be prepared for a lot of false positives. And I mean ridiculously high false positives. In the seizure detection case, when we took a new data set, an animal data set, so we're detecting epilepsy in dogs, and we ran any of the current detectors on it, we would get things like 100 or 500 or 1,000 false positives per true seizure. So this is expensive to manage, right? Even if I just have a queue that I go through. I mean, I may have started with 1 million examples, but 10,000 doesn't help me if I have to process that each day. And finally, there's the concept of adaptation. So as you add new data to your system, new users, as the system evolves over time, you need an element of adaptation. Anomaly detection does adapt in some sense because you've designed it to just represent not what normal is. So as long as your normal class doesn't change, you can handle some degree of adaptation. But in general, your normal class is going to drift too, so you need to account for that. And that adds that whole other layer of complexity to it, which is what makes an anomaly not only with respect to normal, but over time. You know, for instance, do I remember an example from yesterday, or from 10 years ago, or a century ago? Okay, so that's pretty much the summary. If you have questions, I'll take the questions. I have a lot of backup slides if you want to drill into anything. And I just want to remind you to feel free to connect to me. And don't forget about the survey paper. If you or your organization is interested in anomaly detection, this is a great place to start. Even if you ignore all the math and just read the words, it's really good stuff. Yes?
Would you re-explain the concept when you talk about labels? What do you mean by labels?
Okay. So your labels, let's see if I can get there. So when I have an apple and I measure the features, I also know that it's a green apple. The green is the label. And I assign numerical values in the supervised classification problem because that's how I process it algorithmically. Yeah. Did you have someone have a question? Yeah.
Can you talk just a little bit more about the process, your process of featureization? Do you use like expert knowledge, like the doctors who understand this to kind of aid you in that?
So this is a big challenge. Let's see, I think I have a slide on this. If I can find it. So how do you find features? And you know, I'll give you a story from NeuroVista. NeuroVista was the startup that raised $60 million to do this. I don't think I have a slide for that, so I'll just leave it here. They raised $60 million to study seizure prediction, which was an extension of the detection task. And we spent a year looking at how we would find features. And the way we did that is we started with the epileptologists, and we interviewed them. And that worked sort of. I mean, we got some broad brushstrokes of how it happened. But it turned out what was most effective for us was to go canvass all the time series literature. So we looked at earthquake prediction, we looked at bioinformatics, we looked at speech and signal processing, we looked at image processing. We invented features of features. So if you decompose things into, you know, the wavelet or the frequency domain, and you can measure variations on that. Mostly what we found, though, was that key insight that it was spectral changes guided us toward the audio, speech, and signal processing community. And so we pulled a lot of features from that. There are sort of automated featureization techniques. That's kind of a research area. For instance, you can look at things like self-organizing maps and deep belief networks if you want to read on the topic. And these can learn features just from data. So they, I guess, you don't have to read on details any particular implementation, but they're learning basis functions or particular representations that can distinguish.
Sorry, can you just say those two algorithms one more time?
Yeah, so self-organizing maps was an older technique from maybe even the 80s or 90s. It's a neural network technique, and it sort of automatically clusters data sets, and it's been used in time series successfully to get features. You cluster them, and you end up with basically basis vectors, and you project all future time series onto these basis vectors, and the degree of match is what you use as your feature. And deep belief networks are kind of the new trendy topic in machine learning. And this is a neural network architecture that learns through several layers a representational, a feature-wise representation of the data for classification. And I think that the deep belief networks do both the feature selection and the learning at the same time. And so that's what makes them pretty cool, actually. Yeah?
You mentioned something about clustering.
Yeah.
Which clustering algos would you recommend for this kind of application?
So I think without a doubt, the first thing you should look at is an algorithm called TSNE, T-S-N-E. Okay, and this came out of maybe Hinton's lab. I don't remember exactly who came up with it. This is an algorithm that combines dimensionality reduction with whitening and a nice machine learning-based method for clustering. In the paper on TSNE, T-S-N-E, it shows several examples of automatically clustering data sets without any labels. And the example that was powerful to me was the MNIST data set, And the MNIST data set, if you recall, was the opener here. Let's see if I can show you. It's not presenting. Oops. Sorry for the technical challenge here. So it's these handwritten characters, and you can take all 16,000 of these images and run it through the T-SNE algorithm, and the code is available online. The author released it. Maybe this algorithm circa 2008, 2009. And it'll automatically separate the classes into each digit. It recognizes that. And he compares that to other things like local linear embedding, ISOMAP, and a variety of other techniques. And I would say, hands down, it had the most impressive result to me. But, of course, there's always trade-offs, so you may not be able to do it because of computational considerations or things like that. Yeah. Yes?
If you're not dealing with a real-time data set, why would you need to set a threshold? Why wouldn't you just look at the general gradient and decide for yourself what's an anomaly and what's not an anomaly?
Right. So you can. You don't have to have it be a hard decision. You can have a score. I'm posing this as a classification problem because, in general, the end user of these products is someone who's going to have a queue to go work the anomalies. And so in the traditional formulation, things are in the queue or not. In the modern Google search paradigm, right, there's a score. So you can just work the queue in order. Right? But it's a real problem. And in fact, here's another argument for setting a threshold. A lot of times you don't know how your system is going to perform, how the data is going to change, so you don't know how many anomalies you're going to get. For instance, I may be a doctor and see 20 epilepsy patients in one day and none the next. So I can't control how many anomalies I get, but what I can do is I can say that for every good patient that I see, about how many anomalies am I going to expect? And so we set this constant false alarm rate, which says that regardless of how many are actually anomalies, I'm going to accept as a challenge that 5% of my data is going to be something I have to look at. And so that is useful because it allows me to formulate my risk in a very rigorous manner and allows me to allocate resources. So like if I'm a fraud analyst in a bank and I see alerts all day long, I can't process 10 million. Maybe I can only process 200 a day, and that represents 1% of the data. Yeah, other questions? Yeah.
In one of your diagrams, you had referred to using the output to feed, use it for the input again.
Yeah.
Were you referring to reinforcement learning?
That wasn't a reference to reinforcement learning. That would be a great idea. If I was your thesis advisor, let's go. The problem is, and the opportunity is, I don't know of anybody who's done that. I think all the systems that I've seen in academic, in the literature, or in practice, they don't really incorporate feedback learning. It's more of a filter. You sort of like, I'm going to declare, it's Christmas season and you've got a new girlfriend, so you're dropping Benjamins left and right, and I'm going to start flagging you, right? This is not usual. This is not usual. And some analyst in the back end is like, man, I'm tired of calling this guy every week, so I'm going to declare that, when he goes to Victoria's Secret and spends money, that's okay. All right? That's an example of the feedback, right? That's maybe a filtering rule, an override rule. The actual learning of that behavior dynamically, that I don't think has really been done very well because there aren't even that many good examples of online anomaly systems that are more sophisticated than the centroid problem that I was showing you. There are some, but not many. Yeah. Do you have a question? Yeah.
Will you talk more about the novelty detection and why you think that tossing out the seizure data gave you a better model?
Yeah, I'll show you the slide, hopefully. So in novelty detection, so the simple answer is when I don't have the poison apple in this data set, the centroid is located in a different position. If I add the poison apple, it biases the statistics of the data set, right? Unless I'm doing robust statistics, which is, we don't really talk about in anomaly detection. So if I now take the centroid of this new data set, that sphere moves. And so what I've done is misrepresented the normal class, which shows up as an error. So, and in fact, if you go read the original paper by Sholkoff on one-class SVM, it is a novelty detection algorithm. And he calls it that very specifically because it was designed to detect changes. It's like a change point algorithm. I'm just going to assume that I only have good detect data all the time and then look for something that's bad, right? Versus anomaly detection, it's a little different because I may have examples that are bad mixed in, and I know a priori that I'm expecting outlier examples. Other questions? Yeah.
A follow-up on that question. Could you just use a non-parametric means metric like the median so that you can rate this problem?
Well, you can. You can use it, and that's what we show in the which region. For instance, the Tukey statistic, which is the median and the interquartile ranges. I mean, that's a very old, online, 1970s level technology. You can implement it in your calculator. So, and it works. It works pretty well. We did seizure detectors using interquartile range. The problem is that that's also not quite robust, and it doesn't handle cases when you have things like islands. So the neat thing about the one-class SVM is it actually gives you the support where you need it and only where you need it, versus some of these other techniques, which are basically hyperspheres or hyperballs or whatever, that are going to measure a whole region, a continuous region. So, other questions?
Let's have it done. So let's have
All right.
Zito.